In this video, we're going to talk about the complex version of the result from calculus, you recall, where if the derivative is 0, then that implies your function f is constant. So let's recall from Calc 1, what is that result that you're probably more familiar with? So I'll call it lemma 1. If you've got a function whose domain is an interval from a to b and it spits out a real number, so a real valued function, and if it's such that f prime of x is 0 for all x between a and b, so the derivative is 0 for all x between a and b, then that's enough for us to conclude that our function f is constant on this interval from a to b. And let's walk through what's the proof of that look like that, again, you've seen in like a Calculus 1 class. Let x1 and x2 be two elements in our interval from a to b, and let's say x1 is strictly less than x2. And what we're going to do is we're going to apply the mean value theorem. If you'll allow me to zoom in a little bit. The mean value theorem, recall, says that on the left here is the average rate of change of my function from x1 to x2. And that average rate of change, another word for that, or a concept you should relate that to, is the slope of the secant line to the function from x1 to x2. That average rate of change is equal to the instantaneous rate of change somewhere at some c that's somewhere between x1 and x2. Now, by assumption, so the mean value theorem is true, by the way. So for our lemma, the hypothesis in our lemma allow us to use the mean value theorem here. And so now, what else are we assuming in our lemma? We're assuming that the derivative is 0 at all points between a and b. So in particular, it should be 0 at c. So let's substitute that into the equation that the mean value theorem gave us. And that tells me that this average rate of change is equal to 0. And of course, I can multiply through by x2 minus x1 and add f of x1 to the other side to obtain that f of x2 equals f of x1. And if we stop for a moment and think about the fact that x1 and x2 were just two arbitrary numbers that were between a and b, or somewhere in that interval, could be a and b themselves as well. What we've done is we've shown that each input in that interval has the same output. So of course that means that our function is constant, right? Every input has exactly the same output. Now what we would like to do is we would like to obtain a complex version of this theorem. And here's what we think it should look like. So if f is a function from g to the complex plane, so g is some subset of the complex plane, and if it's such that f prime of z is equal to 0 for all complex numbers z and g, then f is constant on g. So it looks the exact same. You notice I just took it and kind of morphed it to fit the complex setting where g is some subset of the complex plane. But here's what we need to be careful about, which was a little bit subtle in the example from Calculus 1. Like notice I took an interval from a to b, right? It wasn't just any arbitrary subset of the real line. And so I need to be equally careful here whenever I try to generalize this theorem to the complex plane. So we need to be careful about what kind of set g is. And so here's an example to show you why. So if I took this piecewise function f of z is -1 if the real part of z is less than 0, and if it's 1 if the real part of z is greater than 0, the domain of this function, it looks like I can plug in anything I want as long as the real part's not equal to 0. And so in this case, the domain of this would be all complex numbers except for complex numbers of the form 0 plus iy, where y is a real number. And just to give you a picture, right, that's the complex plane, but I'm saying that we're not allowed to plug points in that are all along the imaginary axis. So I've drawn that dotted line there to indicate that. And what I want you to notice then was if those are the points that you get to plug in and you're not worried about plugging points in along the dotted line, well then f prime of z, the derivative of my function, it is 0 for all points in the domain. But on the other hand, f is not a constant. And so what is the fix going to be? How do we fix this so that this can't happen? So clearly, like this set G isn't good. It wouldn't be a set that I could use in my theorem up here that I'd like to have. That theorem would not hold for such a G. So what's the fix? How do we be careful? So again, the subtlety in the Calc 1 case was that we did this for an interval from a to b. It wasn't just any set, so there really was the same kind of issue here. So the fix in the complex case is to go ahead and let G be a region. And I colored that word green because region in a complex class, or maybe a topology class even, it has some baggage to it. It's a definition. That means it's an open connected set. So when you see the word region, it's open. So every point inside the set has a little disk centered at that point that's completely contained in the set, and it's connected. So it cannot be split into two non-overlapping open sets. Two non-empty, non-overlapping open sets. So here's what our theorem would look like then. So our theorem would be, let G be a region in the complex plane. Let f be a function from G to C. And if that function is such that the derivative of f is 0 for all points in my domain G, in the region G, then f is constant on G. And that's the theorem that we're going to prove. Now, here's a little note though. What I'd like to do is just recycle the proof from the Calc 1, Lemma 1 up there that you saw in Calc 1. Unfortunately though, we haven't talked about a mean value theorem for functions of a complex variable yet. And so we can't just recycle that proof, right? We don't have the materials to do so. What we can do though is we can invoke a little bit of topology. And so in part 2, in the next video, we're going to go over the topology definitions that we'll need in order to give us the tools to actually prove this theorem that if the derivative is 0, then the function is constant. If the derivative is 0 everywhere, then the function is constant.